Hey everyone, welcome back for another deep dive. We love to really dig into those fascinating research papers, and today is no exception.
Oh, yeah. This one's really cool.
We're diving into Post-Hoc MOTs. That stands for Exploring the Capabilities of Time-Symmetric Multi-Object Tracking. Now, I know that's a mouthful.
It is, but it's pretty descriptive once you unpack it.
Exactly.
Yeah.
So you sent this one over, which means you're probably already knee-deep in the world of tracking, or at least super curious about it.
Definitely. It's a field that's always evolving.
And this paper introduces a way of tracking multiple objects that's pretty mind-bending. We're not just talking about where things are right now.
Nope. It's about using the whole sequence, the past and the future.
So imagine knowing the end of a movie and using that to understand the beginning better. That's kind of the idea here.
It's like having a whole new level of insight. It's not just reacting to what's happening at this moment.
It's more like having this awareness of the whole timeline, which seems almost impossible.
Yeah.
But that's what makes this research so intriguing.
It really challenges the traditional ways of thinking about tracking.
Right, because usually you're trying to predict where something's going based on where it is now and how it's moving.
Yeah, the classic approach.
Yeah.
But as we all know, things don't always move in a perfectly predictable way.
Especially if we're talking about living beings,
Right.
like people in a crowd or cars navigating traffic.
Exactly. There's so much variation and unpredictability.
And that's where this time-symmetric method comes in. It uses the entire video sequence, not just the past frames, to make those tracking decisions.
And that's what gives it such an edge, because it's like having that extra information, that context from the future to inform what's happening in the present.
Okay, so I'm already picturing all sorts of crazy applications for this.
Yeah.
Self-driving cars instantly knowing where every pedestrian and cyclist is going.
Oh, yeah. The potential is huge.
Yeah.
And the paper actually starts with something pretty unexpected. They tested this on microscopic yeast cells.
Yeast cells.
Really? Yeah, it sounds kind of random. But think about it. Yeast
Yeah.
cells are constantly dividing and multiplying, so tracking them is a nightmare.
I can imagine. They're like tiny little rebels zipping around under the microscope.
Right. Exactly. And what's amazing is that this time-symmetric method not only worked on those chaotic yeast cells,
Did excel.
it did. They saw incredible results. And that's what gave them the confidence to try it on something even more complex.
Which was,
Pedestrian tracking in real-world videos, like those crowded street scenes you mentioned earlier.
oh wow. So they went from tiny cells to full-blown human movement. That's a big leap.
It is. But the success rate was similar. They saw this amazing ability of the algorithm to follow individual pedestrians, even when they were briefly obscured by others.
So it's like the algorithm is filling in the blanks.
Hmm.
It's not just seeing a bunch of isolated movements.
It's creating a continuous path for each person, even when they disappear for a few frames.
That's incredible. Now I'm starting to get why this is called time-symmetric. It's like the algorithm is seeing time as a whole, not just a linear progression.
It's like having that bird's eye view of the whole scene, past and future, and using that to make sense of what's happening in the present.
Okay, my mind is officially blown, but I want to break this down even further. So how does this time-symmetric tracking actually work? What's happening behind the scenes?
It's a pretty sophisticated process, but we can break it down into two main parts. There's the part that detects and segments the objects in each frame.
So that's like figuring out what's what in the image. Like this is a person, this is a car, this is a tree.
Right, exactly. And then there's the part that actually tracks those objects through time. That's where the real magic happens.
Okay, so one part is identifying the what, and the other part is mapping out the where and when.
Exactly. And that tracking part has three key steps: local tracking, global assignment, and missing instance interpolation.
Okay, deep breaths. We can get through this together.
I know it sounds technical, but it's actually pretty intuitive. So local tracking is where the algorithm analyzes each object's movement within a small window of frames.
So it's a close-up look at each individual object.
Right, and it's looking both forward and backward in time, so it's capturing those subtle changes in motion.
Gotcha. So it's not just seeing a snapshot of where the object is, it's understanding its trajectory.
Exactly. And then comes global assignment, where the algorithm takes all those individual local tracks and stitches them together.
So now it's creating a continuous path for each object over the entire video.
Right. And this is where knowing the future movements really helps, because it clarifies those ambiguous moments in the past.
So it's like having a puzzle where, the final picture, and you're using that to figure out where each piece goes.
I like that analogy. And finally, there's missing instance interpolation, which is basically filling in the blanks.
So like when that pedestrian gets hidden behind a bus for a second.
Exactly. The algorithm can intelligently predict where they'll reappear based on their past and future movements.
So it's like having a sixth sense for movement. That's amazing.
It really is. And this whole process makes the time-symmetric approach way more robust than the Kalman filter.
No, so now we're getting into the comparisons.
Yeah.
The Kalman filter is like the OG of tracking, right?
It's a classic, and it works great when things move in a nice, predictable way, but real life is rarely that simple.
Yeah, it's messy and unpredictable. People swerve, cars stop suddenly.
Exactly. And that's where the Kalman filter starts to struggle. It's too rigid. It can't adapt to those sudden changes.
So it's like trying to fit square pegs into round holes.
Kind of. And the researchers designed a really clever test to highlight this. They created a visual signaling scenario.
Okay, I'm intrigued. Tell me more.
They had these animated arrows that changed color before turning, like a car's turn signal.
So it's like they gave the arrows a way to communicate their intentions.
Exactly. And they wanted to see if the algorithms could learn from those visual cues.
So it's not just about physics anymore. It's
No.
about understanding the meaning behind the movement.
And the results were really telling. The Kalman filter struggled as the arrow's movements became more reliant on those signals.
It's like it couldn't grasp the concept of signaling.
But the time-symmetric approach handled it like a pro, because it was able to look ahead and see what the arrow was going to do.
So it's like having that insider information, that future context.
Exactly, and that's what gives it such an advantage.
Okay, so we've seen how this time-symmetric method works, how it compares to other approaches. But I'm curious about the inner workings. How do the researchers actually see what the algorithm is doing?
That's a great question. And they actually use a technique called attention analysis.
Attention analysis.
Wow.
What is that? Like a therapy session for algorithms?
Not quite. It's a way to visualize what the algorithm is focusing on when it's making its tracking decisions.
So instead of just seeing the final output, they can see which parts of the image the algorithm is paying attention to.
Exactly, like a heat map showing its areas of interest.
Wow, that's really cool. So it's like peeking inside the algorithm's brain.
In a way. And what they found was really fascinating. The algorithm was picking up on these subtle patterns and visual cues that weren't explicitly programmed into it.
So it's like it's learning on its own. It's developing its own understanding.
Exactly. And that suggests that it's doing something similar to what our brains do when we process visual information.
That's incredible. It's like the algorithm is mimicking human intuition.
And that opens up a whole new way of thinking about how these algorithms work and how we can improve them.
This is definitely some next level stuff.
It is, and there's so much more to explore.
Well, I can't wait to dive even deeper. So stay tuned for part 2 of this deep dive. We'll be back with even more insights and analysis.
I'm ready when you are.
So we just left off talking about how this algorithm is like getting these little glimpses into the future to make better tracking decisions in the present.
Yeah, it's like it's got a little bit of a cheat code.
But the thing is, it's not cheating. It's actually using all the available information to make the most accurate assessment.
Right, and that's what sets it apart from those traditional methods that are just kind of stuck in the moment.
Exactly. So before we went for a quick break, we were about to compare this time-symmetric method to some of the more advanced tracking systems out there.
Yeah. Let's pit it against the heavy hitters.
Because we want to know how it really stacks up. Like, is it just a cool concept or is it actually a contender?
It's definitely a contender. And the researchers actually went head-to-head with a state-of-the-art tracker called Tractor.
Tractor. Okay, so we're talking big leagues here.
Yeah, this is a well-established system. It's used in a lot of real-world applications.
So it's like the reigning champ.
Exactly. And they put both systems through their paces using a data set specifically designed for challenging multi-object tracking scenarios.
So they didn't pull any punches. It was a real test.
Nope. They threw everything at them. Crowded scenes, occlusions, fast movements, the whole 9 yards.
Okay, and drum roll, please. What are the results?
Well, both systems performed well overall, which is to be expected. They're both top-tier trackers.
So it wasn't a total knockout.
Not exactly, but the time-symmetric approach did show a distinct advantage in one crucial area.
Which was?
Associative tracking accuracy. That's basically how well it can connect the dots between objects across different frames.
So even when things were getting obscured or moving erratically, this new method could still keep track of which object was which.
Exactly. It was better at maintaining those individual identities.
And that's super important, right?
Yeah.
Especially if we're talking about real-world applications, like autonomous vehicles.
Oh, absolutely. Imagine a self-driving car navigating a busy intersection.
Yeah, with people darting across the street, cyclists weaving through traffic.
It's chaos. And the car needs to not only track where everything is going, but also understand who's who and how they're all interacting.
So it's not just about avoiding collisions. It's about anticipating movements and making smart decisions based on those predictions.
Precisely. And that's where that high associative tracking accuracy really comes into play.
It's like having a sixth sense for traffic flow.
It's amazing stuff. And it's not just limited to self-driving cars. We could use this in security camera footage analysis.
Oh, yeah. So instead of just recording what's happening, you could actually have a system that's analyzing and understanding the scene in real time.
Exactly. And that could have huge implications for things like crime prevention and public safety.
Wow. The possibilities are endless.
They really are. And we haven't even touched on things like medical imaging.
Oh, yeah. Imagine being able to track the movement of cells in the body.
Or monitor the flow of blood through the circulatory system.
That could revolutionize diagnostics and treatment.
And even things like sports analysis. Imagine being able to track every player on the field with pinpoint accuracy.
That would be incredible. You could get all sorts of new insights into game strategy and player performance.
It's mind-blowing stuff.
Okay, so I'm sold on the potential. But I have to ask about the practical side of things. How computationally demanding is this method?
That's a good question. And it's definitely something the researchers addressed in the paper.
Because all this fancy tracking can't be free, right?
It does require more computational power than some of the simpler methods, especially when you're dealing with longer video sequences.
So it's like the more data you feed it, the harder it has to work.
Kind of. But the researchers actually did a lot of work to optimize the architecture to make it more efficient.
So they weren't just focused on the theory. They were also thinking about the practical implementation.
Right. They significantly reduced the memory usage and processing time, so it's becoming more and more feasible for real-world scenarios.
That's great to hear.
Yeah,
Because it's one thing to have a brilliant idea, but it's another to actually make it work in practice.
exactly. And they're bridging that gap.
Okay. So we've talked about how it works, how it compares to other methods, the computational challenges, but I want to zoom out for a second.
Okay, let's take the wide-angle view.
If this method can track yeast cells in pedestrians, what other applications can you envision?
That's where things get really fun, because the underlying principles of this time-symmetric approach are so broadly applicable.
So it's not just a one-trick pony.
Nope. We could track traffic flow, analyze animal behavior in the wild, even monitor the movement of celestial bodies.
Whoa, okay. Now you're really blowing my mind.
It's like we're opening up a whole new window into understanding the world around us.
It's not just about observing what's happening. It's about understanding the patterns and the interactions over time.
Exactly. And that's where the real power lies.
So we're moving from observation to prediction to true understanding.
That's a great way to put it. It's a fundamental shift in how we approach tracking and data analysis.
This is seriously groundbreaking stuff.
It is. And the researchers are really pushing the boundaries of what's possible.
Okay, so I'm completely on board with the excitement. But I'm sure there are still areas for improvement. Did they mention any limitations or future directions for this research?
Of course. Every breakthrough has its next step.
Because there's always room to grow.
Right. And one thing they highlighted was the importance of the instance segmentation step.
Okay. Remind me what that is again.
That's the part that identifies the individual objects in each frame, like saying, this is a person, this is a car, this is a tree.
Right, so it's like the foundation of the whole system.
Exactly. And the accuracy of that initial segmentation directly affects the performance of the entire tracking process.
So it's like if you start with a blurry image, it's hard to get a clear picture no matter how good your tracking algorithm is.
That's a great analogy. And while they used a very capable model for this segmentation step, they acknowledged that further improvements are definitely possible.
So it's like they're saying, we built this awesome car, but we could still upgrade the engine.
Exactly. And they suggested tailoring the training process to specific scenarios or object types.
So like having a specialized engine for city driving versus off-roading?
Right. And they also emphasized the importance of exploring new instance segmentation models that might be even more accurate and efficient.
So it's like they're inviting others to join the race and push the boundaries even further.
Exactly. That's what's so great about this research. It's not just a finished product. It's an invitation to collaborate and innovate.
It's the start of a whole new journey.
It really is. And it'll be fascinating to see where it takes us next.
Okay, so we've covered a lot of ground here. We've gone deep into the technical details, explored the potential applications, even talked about the areas where it can be further improved. But I want to step back for a moment and ask you as an expert, what's the most striking aspect of this research? What really stands out to you?
That's a tough one. There's so much to admire, but I think the most remarkable thing is the conceptual shift it represents.
The conceptual shift.
Yeah, this isn't just a minor tweak to existing methods. This is
Yeah.
a whole new paradigm for thinking about tracking.
It's like they're rewriting the rule book.
Exactly. And that's what makes it so exciting. It opens up possibilities we hadn't even considered before.
Like, what are some of those possibilities that are now on the table?
Well, imagine a world where we can track the movement of everything with incredible precision,
Everything.
from the tiniest particles to the largest celestial objects.
Wow, that's kind of mind-blowing.
It is. And that's the potential this research unlocks.
It's like we're on the verge of a whole new era of understanding movement and interaction.
It's a pretty amazing thought.
It really is. Okay, so as we wrap up this part of our deep dive, I want to leave our listeners with something to ponder.
Always good to have a little homework.
Right. We've explored the technical details, the potential applications, even the philosophical implications. But what's the one takeaway you hope they walk away with?
I hope they grasp the transformative potential of this time-symmetric approach. It's not just about tracking objects more accurately. It's about fundamentally changing how we perceive and understand movement interaction and even time itself.
Beautifully put. It's a reminder that innovation often comes from challenging our assumptions and exploring new ways of thinking.
Exactly. And who knows what other groundbreaking discoveries await us as we continue to delve into the mysteries of the world around us.
That's the perfect note to end on. A huge thanks to our expert for guiding us through this incredible research.
It was my pleasure.
And to our listeners, keep those questions coming. Until next time, stay curious. You know, as we're talking about this, it almost feels like science fiction is becoming reality.
It really does.
Like we're breaking down those barriers between what we thought was possible.
It's like we're stepping into a whole new dimension.
Exactly. And it's all thanks to this time-symmetric approach.
Huh.
But there's one aspect we haven't really touched on yet. And it has to do with how this technology could impact our understanding of something pretty fundamental.
Oh, yeah. What's that?
Visual perception. How we actually see and make sense of the world around us.
That's interesting. I don't think we've gone there yet.
Because think about it. This algorithm is analyzing an entire video sequence, past and future, to make sense of what's happening right now.
Right. It's like it's got this holistic view of the scene.
Exactly. And that's kind of similar to how our brains work. We don't just process visual input in this linear fashion.
Nope. We're constantly using context and memory to interpret what we see.
Right, like if you see a ball rolling towards you, you don't just react to the immediate image. You also use your knowledge of physics, gravity, and past experiences to anticipate where it's going to go.
Exactly. We're always drawing on these mental models to make predictions and guide our actions.
And this algorithm, by incorporating information from the entire video sequence, seems to be doing something similar.
It's like it's building its own internal model of the world.
And that's what I find so fascinating. It suggests that there are these parallels between how this algorithm works and how our own visual system functions.
Yeah. It's like we're starting to understand the brain by looking at how we can build machines that can see.
Exactly. And if we can figure out how the algorithm achieves this level of understanding,
It could lead to all sorts of breakthroughs in fields like computer vision and AI.
and maybe even help us understand those mysteries of the human brain a little better.
Right. It's like a two-way street. We're learning from the machines, and the machines are learning from us.
Okay. So as we wrap up this incredible deep dive into the world of time-symmetric tracking, I want to leave our listeners with something to ponder.
A little food for thought.
Exactly. We've explored the technical details, the potential applications, even those mind-bending philosophical implications.
We've really gone down the rabbit hole.
We have. But what's the one takeaway you hope our listeners walk away with?
I hope they understand that this isn't just about tracking objects more accurately. It's about fundamentally changing how we perceive and understand movement interaction, even time itself.
Beautifully put. It's a reminder that the most groundbreaking innovations often come from challenging our assumptions and venturing into uncharted territory.
Exactly. Who knows what other amazing discoveries await us as we continue to explore these new frontiers.
Well said. A huge thanks to our expert for guiding us through this incredible research.
It was a pleasure.
And to our listeners, keep those questions coming. Until next time, stay curious.